Hi, I'm Maura, America's Regional Marketing Manager for Trace Elemental Analysis. In this presentation, we will cover trace element speciation using IC-ICP-MS analysis of lithium-ion battery degradation products. Today's society is very mobile, and with this comes an increasing need for portable energy sources. Batteries allow us to generate electricity when and where we need it. As our need for portable energy continues to grow, so too does the demand for better battery technology. Many different types of batteries are produced for a wide variety of applications. Some devices, such as portable electronics and power tools, use very small batteries. Others, such as hybrid vehicles, use much larger batteries. The individual requirements, potential, capacity, discharge rate, etc., vary with the intended use. Battery-operated devices have become such a dominant part of our routine lives, it's a wonder what we would do without them. Batteries have been around since the year 1800 when Alessandro Volta first generated electricity using alternating zinc and copper discs that were separated with an electrolyte consisting of brine-soaked cardboard. However, those batteries, much like the Duracell or Energizer batteries we're used to purchasing at the local store, share a key drawback: they're disposable. In a simplistic view of its operation, a typical consumable battery consists of a positive and a negative electrode. The two electrodes are separated by a liquid or dry chemical electrolyte. When the two ends of the battery are connected to an electronic device such as a light bulb, a series of chemical reactions is initiated. The reactions generate a buildup of positive ions at the positive electrode and a buildup of electrons at the negative electrode. To maximize the distance between one another, the electrons travel through the electrical circuit and the light bulb to reach the positively charged electrode. The electrolyte inside the battery acts somewhat like an insulator, so the path of least resistance for the electrons is through the external circuit. Disposable batteries provide safe, inexpensive power for all your electrical devices which cannot be tied down with a power cord. However, the chemical reaction that takes place inside the battery has a limited lifetime and cannot be reversed, which means the battery cannot be recharged and reused. As the chemicals are depleted, the battery's power dwindles until it eventually fails. Those chemicals also make battery disposal environmentally unfriendly. In response to the limitations of disposable batteries, rechargeable batteries were developed. Rechargeable batteries have gone through a number of design iterations to address power output, safety, cost, and environmental impact, and the lithium-ion battery design has become the most popular for its ability to address those considerations. Lithium-ion batteries have widely replaced nickel-metal hydride batteries in a number of applications. Rechargeable batteries offer several benefits to the consumer. They possess a high energy density which allows them to produce the same or greater output voltage as a lead-acid battery, but in a smaller, lighter weight package. The batteries have no significant memory effects and lose minimal charge when not in use. With proper handling and use, lithium-ion batteries will last several years before needing replacement. Lithium-ion batteries can store twice the energy of a nickel-based battery and 4 times that of a lead-acid battery, and as the name suggests, a lithium-ion battery operates based on the movement and transfer of lithium ions. When the battery is being charged, lithium ions flow from the cathode through the electrolyte and are reduced back to lithium metal at the anode. At the same time, electrons flow from the cathode to the anode. However, the path of least resistance for the electrons is via the external circuit instead of through the electrolyte. When the battery is being discharged to supply power to an electronic device, the lithium in the anode is oxidized to form lithium ions, which travel through the electrolyte material to the cathode. The cathode, which is composed of a lithium metal oxide material, oxidizes to create a compound that can store the arriving lithium ions. At the same time, electrons flow from the anode to the cathode. However, they travel via the external circuit and through the electronic device that's connected to the battery. Even though a considerable amount of work has been done on the development and commercialization of lithium-ion batteries, there is still considerable interest in improving the current technology and the development of new battery components. In order to investigate how the battery cells are aging, there are at least two different components to look at: the electrolyte and the anode. The most highly used electrolytes are organic carbonates like dimethyl carbonate, methyl ethyl carbonate, and so on. Through thermal stress on the battery cell, the electrolyte can undergo a variety of reactions as shown in this image, which leads to the loss of cyclable lithium and hence to a reduction of the battery capacity. The other component to look at is the anode material. Through the charging process, and especially if the charging voltages are elevated in order to reduce charging times for the battery cells, oxidation of the cathode material can occur so that metals which are actually part of the cathode are deposited on the anode and are no longer able to travel back. This also reduces the battery capacity. The subsequent slides will highlight results that were obtained through the analysis of different anode samples. There is a great deal of interest in this particular market. As shown here, sales to the electric vehicle segment alone were $3 billion in 2012, and they're estimated to reach nearly $23 billion by 2020. Driving that demand is the adoption of hybrid electric vehicles, which likely will be followed by regulations for improved fuel efficiency and reduced exhaust emission, ultimately leading to sales of electric-only vehicles. As a result of this demand, there are reports of investments being made in R&D to improve battery performance, longevity, and safety. A particular strategy being employed is identifying degradation products and understanding battery degradation mechanisms. Understanding failure analysis requires analysis of the three battery components, individually and how they interact as a system. Today's presentation centers on degradation products resulting from the interaction between the electrolyte and the anode, which comprises nearly 33% of the chemicals and materials market. As mentioned previously, much research has been spent on improving product safety, cycle life, and power output of lithium-ion batteries, yet understanding fundamental processes and degradation mechanisms that take place within them remains a challenge. The work presented here will describe the identification of electrolyte degradation products deposited on the anode surface of a cycle-aged lithium-ion battery using a portfolio of analytical products. Results are based on analysis using ion chromatography with high-resolution mass spectrometry, and ion chromatography with IC-ICP-MS. Here we illustrate the workflows relevant to lithium-ion battery analysis. The workflow indicates which analytical techniques are suitable for use given the analytes and battery properties that are to be measured. Products include chromatography, mass spectrometry, atomic absorption spectroscopy, and molecular spectroscopy instruments, all of which can be used in research, development, or production environments. As indicated here, there is no single analytical instrument that provides results for all of the components and processes relevant to lithium-ion battery operation. To investigate processes that will improve battery safety, lengthen the lifetime of the battery, and increase its power output, a variety of instruments and technologies will be needed to fully understand battery degradation processes and failure mechanisms for each battery component individually and how they interact together as a system. An example of lithium-ion battery analysis using ion chromatography high-resolution mass spectrometry is shown here. In this work, a thermoscientific Q-exactive Orbitrap mass spectrometer provides component identification of lithium-ion battery degradation products in untargeted and unknown workflows. Results from the analysis of electrolyte degradation samples by ion chromatography using a potassium hydroxide eluent and suppressed conductivity detection is shown on the left. On the right, mass spec results were generated from the extracted ions of a full scan taken of a peak at 3.78 minutes using high-resolution mass spec in a negative ion mode. Shown are degradation products with experimental mass-to-charge ratios ranging from 110 to 180. Elemental composition was based on high-resolution accurate mass data. The table on the far right shows elemental composition possibilities. The peak at a mass-to-charge ratio of 125.0004 is consistent with a proposed structure of dimethyl-phosphate anion. With 4 decimal point accuracy, the use of high-resolution mass spectrometry provides a high level of confidence in the identification of the degradation product and quickly eliminates thousands of alternate possibilities. In order to confirm the findings previously presented, the same separation was performed using inductively coupled plasma mass spectrometry as a detection system, instead of the high-resolution mass spectrometer used in the previous example. Although IC-MS is not able to provide structural identification for a given compound, it can unambiguously indicate the presence of a given element, in this case phosphorus, and quantify its exact amount. This slide shows how ion chromatography coupled to the thermoscientific ICAP-Q-ICP-MS provides identification of phosphorus-containing lithium-ion battery degradation products in the presence of other elements. Results from the analysis of a second electrolyte degradation sample by ion chromatography under similar potassium hydroxide eluent conditions is shown on the left. Shown on the right are results for the analysis of phosphorus using IC-ICP-MS. There are 4 main peaks, one of which is suspected to be the previously identified compound dimethyl phosphate. Elucidating the structure of the remaining peaks is still a work in progress. As mentioned in the previous slide, an ICP-MS won't provide structural identification for a given compound. However, it can quantify all elements present. Let's discuss the operation of the ICP-MS. A schematic of the ICAP-Q series ICP-MS is pictured here. The front end of the ICAP-Q allows for easy access to the sample introduction components and the torch for rapid assembly and disassembly. The ICAP-Q also uses a high-efficiency RF generator which operates at 27 MHz with an efficiency of over 78% to generate a rugged and stable plasma. The interface region provides easy access to the sampler and skimmer cones, as well as the extraction lens and the plasma load coil, should it be necessary to access these components. The interface region is where the pressure inside the instrument is gradually stepped down using a rotary pump and a turbomolecular pump. The ICP-MS has a spectrometer that is maintained under vacuum to reduce background levels and improve ion transmission. Once the ions pass through the interface region, they are filtered with the right-angle positive ion deflection or rapid lens. This lens deflects ions by 90 degrees. Neutral atoms and gas molecules, unaffected by the lens's deflection, pass straight through the lens and are prevented from traveling through the rest of the instrument. This step improves the stability of the collision cell and reduces background levels when the ions reach the detector. After deflection with the rapid lens, ions travel to the Q cell. The Q cell is a high-efficiency collision cell which uses kinetic energy discrimination and low-mass cutoff to reduce polyatomic interferences. The Q cell contains a flatopole with a reduced cell volume to improve ion transmission and to allow the cell to be rapidly pressurized and flushed during sample analysis. The mass filter is a quadrupole that efficiently filters all incoming ions to allow rapid sequential transmission to the detector, which is linear at over 9 orders of magnitude. The detector is a consumable item and will need to be replaced during the instrument's lifetime. The instrument allows easy access to the detector, which is modular, allowing easy and rapid replacement with almost no instrument downtime. So how do we couple the ion chromatograph to the ICP-MS to provide a seamless, user-friendly workflow? Let's look at that in more detail here. A simple piece of hardware connects the 2 instruments. The outlet of the analytical column is directly connected to the nebulizer of the ICP-MS. Inert tubing with a narrow inside diameter is used to make the connection between the 2 instruments. The narrow inside diameter is important in minimizing peak broadening as solution travels from the IC column to the ICP-MS. There's never usually any need to dilute or split the IC eluent, as the ICP-MS has a robust source and is able to handle a range of flow rates and different mobile phase types. The IC system itself utilizes reagent-free ion chromatography eluent generation. The eluent is produced online at the point of use through the electrolysis of water and is suitable for both anion and cation exchange separations. The Thermo Scientific IC-ICP-MS system also boasts a single software interface for both systems. The Chromeleon software that operates the IC is integrated into the Qtegra software which operates the ICP-MS, giving the user full control of both instruments through a single interface. This enables a fully integrated setup with a single operating method. No trigger is necessary. This topic is of particular interest to manufacturers of battery cells who are affected by battery cell degradation. The data presented here is based on a collaborative effort between Thermo Scientific and a lithium-ion battery manufacturer. The customer collected data using ion chromatographic separation with ESI Tandem mass spectrometry detection. Their data collection efforts were useful in producing structural identification. However, the technique was unable to confirm the presence of elements such as manganese, cobalt, and phosphorus. Thermo Scientific provided results based on ion chromatographic separation with IC-MS detection to provide complementary results to those that had been collected by the customer. Samples of 2 different types of lithium-ion battery anodes were received for this work. Batteries were received from the automotive sector and from a variety of devices used in consumer electronics products. It's important to note that the composition of each cell is slightly different, which will be reflected in the results. For each type of sample, 3 anode samples were received: control anodes, in which no aging was expected to have taken place; calendar-aged anodes, which had been aged by storing them under controlled storage conditions for a set period of time; and cycle-aged anodes, which were aged by undergoing repeated charging and uncharging cycles. This picture shows you what a typical sample looked like. As seen here, the sample consisted of a thin graphite layer on a copper foil support. The dimensions of each sample differed due to the different applications of each cell, but the basic design was similar for all cells. For sample preparation, pieces with more or less equal weight were cut and prepared as shown in subsequent slides. All anode samples were prepared according to the procedure outlined here. The procedure was developed by one of the manufacturers who submitted samples for analysis and is based on a 3-step extraction using millicu water. First, a piece of the anode weighing between 0.5 and 1 gram was immersed in 10 milliliters of millicu water and sonicated in an ultrasonic bath for 30 minutes. The extract was removed and stored, and the anode was covered with a fresh 10 milliliter volume of millicu water. Once added, the solution was allowed to stand for 30 minutes. The extract was again removed and stored, and this second step was repeated. All 3 extracts were collected, combined, and filtered using a 0.45 micron membrane syringe filter. The filtered solution was diluted 20-fold with millicu water and analyzed on an IC-MS. The photo shown here depicts, from left to right, extracts for a control anode, a cycled anode, and a calendar-aged anode, respectively. Based on the visual difference in color between the solutions, it's reasonable to assume that each anode type will produce a measurably different target analyte ratio. The results for the submitted samples are shown in this table. Results for lithium, boron, and iron indicate that there was no significant difference in the concentrations for these elements in the 3 types of anode samples. This would indicate that the concentrations of lithium, boron, and iron are independent of the age of the anode and do not change as the anode ages. Results from manganese, cobalt, and nickel indicate that the metal concentration increased with the increasing age of the anode sample. The concentrations of these elements were highest in the cycle-aged anode, indicating that the cycle-aged anode had experienced the greatest wear and tear. A relatively high concentration of phosphorus was found in all samples. However, upon further investigation, the high concentrations were found to be due to an error in sample preparation. A crucial rinse step to remove remaining electrolyte solution from the anodes was accidentally skipped. This will be discussed in further detail later in the presentation. As mentioned before, due to the high amount of phosphorus that was found in the total element quantification, phosphorus was also measured during anion exchange separation of the anode extracts. What could be happening in lithium-ion batteries is that through thermal degradation of the electrolyte, mostly organic carbonate like dimethyl carbonate or ethyl methyl carbonate can react with the anion of the conductive salts, which in this case is hexafluorophosphate, to form different hydrolysis products. This leads to an increase of the cell impedance and a loss of cyclable lithium. In this study, we did not aim to identify the different hydrolysis compounds, but these had been described previously using a hyphenation of ion chromatography and IC-ICP-MS. It's important to note that the chromatogram for the cycle-aged anode clearly indicates a change in peak profile when compared to that for the control anode sample, where no aging is expected to have taken place. A similar change in peak profile is observed when the chromatogram for the calendar-aged anode is compared with that for the control anode. Results for manganese indicate that the concentration found on the anode increases as the battery age increases. The manganese on the anode is originally from the cathode and has undergone an irreversible oxidation which causes a loss of cathode material and ages the battery cell. Anion exchange results indicate that chromatographic separation for individual manganese-containing species was not achieved. However, the fact that the species was retained on an anion exchange column indicates an anionic species. That observation, coupled with results from ion chromatographic UV measurements and cation exchange experiments, support the theory that the eluted species was the permanganate ion. Results for the anodes from consumer electronics products were slightly different from those from the automotive sector. Unlike the previous anode samples, which contained predominantly manganese, anodes from consumer electronics produced degradation products which contain mostly cobalt. This is expected as each industry demands different performance characteristics from a lithium-ion battery, which means that each cathode material is different. In the automotive industry, cathodes contain mostly manganese to enhance their performance. In the consumer electronics industry, price is an important factor, so cathodes typically contain a mixture of cobalt oxides. During degradation, therefore, an irreversible oxide of cobalt to cobalt-4 is typically observed. As indicated here, a different column was used than that for the previous separation. The column used here was chosen to maximize the separation of cobalt-containing species. Results for two of the submitted samples will be compared here. For ease of comparison, the circled mass in each chromatogram indicates the amount of sample that was extracted to produce that chromatographic result. As indicated here, sample A contained relatively high concentrations of cobalt in the anode extracts, indicating that the battery was considerably degraded. When sample C was analyzed, the control anode produced a chromatogram nearly identical to that for sample A. However, the cycled anodes already showed signs of surface corrosion in the form of a white coating. For that reason, it was decided that the corroded and non-corroded parts of the battery would be analyzed separately. Results in the chromatogram on the lower right indicate that the white-coated corroded part contained high levels of degradation products when compared to the results for the non-corroded part of the battery. Results for manganese and cobalt in sample B are presented separately from those in samples A and C. The reason for this is sample B showed heavy corrosion on the surface of the anode, which led to damage when the separation layer between the cathode and anode was removed. The damaged and undamaged parts of the cell were analyzed separately. Results for manganese and for cobalt are presented in the chromatograms with the green and the blue traces respectively. Chromatograms for the damaged components are listed on the top, and those for the undamaged components are on the bottom. As indicated in the chromatograms, the degradation products didn't contain significant concentrations of either cobalt or manganese. Two conclusions that can be drawn from these findings are: the first conclusion is that the lithium-ion cell is of good quality and was able to resist an irreversible chemical modification of the cathode, even under corrosive conditions. The other possible conclusion is that the wrong analytes were targeted for measurement during the analysis of this particular cell. In summary, IC-MS is a simple and highly efficient tool to detect and quantify the extent of degradation caused by changes in the trace elemental composition of lithium-ion battery samples. IC-MS can unambiguously identify the presence of certain elements in the elution profile of an ion chromatographic run. Ion chromatography coupled to IC-MS can help identify degradation species and explain degradation pathways.